Good afternoon. I don't like my voice in the microphone. Closer. Okay, good afternoon. It's a pleasure to have here Professor, I don't know if I can speak correctly his name, Ciesielski? No?
Yeah, that's...
It's still wrong, right?
Chris.
Chris. So Professor Krzysztof Ciesielski, he's a friend actually and a collaborator in the thematic project that we have for PESP, and he has we have worked on some we have some works together at the maybe 2 or 3, more than 3 papers probably.
3 or 4, I think.
Yes, so we have collaborated for some years now, and he has come to Brazil every year at least. Or last year you didn't, but he should be here every year or at least every 2 years. So it's always a pleasure when he's here. So he has a background in pure mathematics, so he did the master and PhD in Warsaw University in pure mathematics, and now he has a double appointment, so he's professor at the West Virginia University in the United States, and he has another appointment at the Department of Radiology in the University of Pennsylvania. And his research interests in pure mathematics, of course, and applied mathematics, more in image processing, image segmentation. So the talk today will address the problem of the image segmentation problem. And the title of the talk is Efficient Algorithms for Max Norm and Lexicographically Optimized Labelings. So I hope you enjoy and participate, asking him a lot of questions.
Okay, thank you. I have this, so you can turn this off. So maybe first of all, there's kind of echo. Is it okay? Okay. First of all, this particular talk is basically should be considered as a kind of from the tier of algorithms. I will talk specifically about 2 relatively new algorithms, but also relate to some others. Most of the time when I give the talks, I actually have some experimental results, but this time it's pretty much too new, and there are quite a few still ideas about theory, so we decided to spend more time on developing theoretical aspects. I'll give you some kind of suggestions where we can do applications. Algorithms are actually not that difficult, so it is very likely that if you know it, you can try find your own application. So I might just give you some kind of general idea. So what's all about? So I will talk about background, and when I talk, well, on the first bullet has background word in it, but actually the first 2 bullets are about background. So I'll generally tell you about labeling. Actually, we think, and more, especially in this group, usually labeling is the segmentation, but it can be used in some other settings. So like a lot of algorithms, you can use them in one settings, but also in the others. And then I'll talk a little bit about actually transition of the old research into new research, the new algorithms, and then some other possible twists. Okay, I encourage you to ask questions. This is I usually try not to give too many slides. I think it is better if you don't see all the details, but rather the whatever you see that it stays. Okay. Okay. So what's the background? In general, this is kind of very overview background. There's a lot of fundamental problems in image processing, computer vision that can be solved by optimization. Actually, this particular style sentence was done by, I believe, Philip one of my co-author, but this list isn't by no means exhaustive. Actually, you can go well outside image processing. In this particular case, we'll be talking about algorithms that talks about labeling, and in a moment I will tell you more or less what I understand by it. But if in the standard image processing, you can imagine that you have image, so it is represented by pixels, and usually like to in the labeling, let's say I call this in the two objects. This will be the most, what I will be emphasizing in this word. So I like to split the image into two parts. One we will be having label 1, another label 2. If you're talking about segmentation, this will be referred to segmentation, but if it is used for, I don't know, in registration, for example, we don't think about this necessarily as a segmentation. And this is kind of standard thing. We identify image with the graph. I do this because most of the methods actually we nowadays represent the graph language. Actually, these methods are slightly more general, so go slightly beyond the graph theoretical representation, but actually it can be still viewed as a graph. Okay, f of s will be image intensities, and by labeling we will just the mathematical denote as a function that for every vertex associate some number. Okay. Okay, so that's kind of easy. When you talk about an optimization, you need to have some function that you optimize, and in general, there's a lot of functions, so you cannot have algorithms for all of them. So we like to kind of describe specific set of energy functions or cost functions that we would try to optimize. Before I'll tell you what the energy, I like to talk about what is called a local cost map. That's actually quite common in image processing in general. So the standard, the local cost function is connected with just image attribute, basically either intensity at the pixel or nearby. Okay. So in the unitary terms, we think about that for every pixel we associate some energy or cost. And so we can kind of imagine that, for example, if your object 1 is supposed to have some intensity called 100, and this a pixel has cost 105, so then the cost of assigning this to the label 1 to this axis should be low, yes, and high to the 0. So this gives you some kind of idea. So we have this cost. But again, when I talk about costs, we have the following. We have vertex, its label, and actual cost. So we have basically three objects. And then we'll also talk about pairwise terms. And usually you can think about pairwise terms. Actually, the first one can easily translated into vertex-weighted graph. Okay, when you have vertex-weighted graph, basically we have something of this kind. In the second, we have, well, if you are talking about two labels, we have four possibilities of labeling. In the most general setup, I don't impose any restriction on these numbers. Sure, in most of the application, 0, 0, and 1, 1 uniform are usually associated with 0. Okay. Also, in other cases, when you talk about undirected graphs, these two ones will have the same costs, but up front we are assuming nothing. Well, let's say for convenience we assume that these are non-negative numbers. We can even leave this, but it will be a little bit easier to think that these are non-negative numbers. So these are local costs. Well, you've probably seen this before. The question is how to gather them together. So one of the way and what you can do is translated this local cost, so some local attributes, so some global information. And the only technique we actually have when you optimize is optimize some global energy. And the one of the typical energy we like to talk about is just taking a sum of these guys. But what these things are means? Notice that I'm putting here L of S. So when we have actual labeling, we don't take both of these atoms, but only I call this atom. So the information, the cost of the vertex that's associated with actual label, okay, not just theoretical things, and then look for the cost of actual labeling of an edge. And in this particular case, I suggest take a sum. Actually, the sum is not my main interest, but this is the background. This is where actual previous research has been done. So I'd like you to see some general connection. Okay. Why I call this, there is this kind of strange symbol in double bar and 1. This is something sometimes connected to mathematical notion of L1 norm. Basically, L1 norm is when you add the pieces together, simple addition. In a moment, I will also talk about L2. L2 is basically Euclidean distance. So you square the distances, they take the square root. At some point, I will talk a little bit about more generalization, but these are kind of standard ways of adding some kind of, I don't know, errors or something. These last things I like to mention, this is the same formula. There's an old paper in 2004 that I'll refer in the next slide. They usually use this other representation. I decided to move to the red one because I like to talk about this L norms, and this is hard to see that it has something to do with the norm. So their notation was not, it's okay for implementation, but not very good for theoretical discussion. So I slightly changed this. Okay, so one more thing. Here I mentioned about LP norms. So for example, if P is 2, we'll take some squares of them and then take a square root of it. This kind of norms LP for different values of P, but basically for P between 1 and infinity it can be defined. For P equal infinity it's not well defined, so I need to tell you separately what that means. I'll tell you in a moment why I like to mention this in general. There's only, we won't be talking much about it, but there's kind of natural transition from one sort of problems to another. Usually we talk about only two extreme points, either 1 or infinity, but to see the difference, it is kind of good to see the connectedness. But actually I think that this makes the value also for some other values of P. Okay.
The whole idea is actually to minimize that equation, right?
Well, it means right now I'm talking about different ways of defining. When you're talking about optimization, you can either maximize or minimize. In this particular case, since we kind of consider this as pseudo distance, we like to minimize. It is easy to create distance as large as you like, yes? So the minimization is the natural statement, okay? So this is kind of, again, if you like to think about P, take P equal 1, you'll know summation. P equal 2, this Euclidean distance. What's happening in infinity? Well, suddenly you don't have P's, and I tell you, take a maximum of all of these guys. This is actually not very intuitive, but what's known in analysis, and actually, if you take even pre-calculus, if you know what's the definition of the limit, and in about 1 or 2 lines, I can show you that when P goes to infinity, that this expression goes to this expression. Okay. So this is kind of natural way of doing it. I'll be mainly interested in this particular cost. The reason is this was actually used in some version for many years in image processing. One of the reasons is because actually it has both algorithmically very nice properties, but also theoretically it has very nice properties. So this would be my main interest, but I talk about both of them still because I like to maybe let's say, what's the value of P? What's the meaning of it? Well, the value of P kind of controlling the balance between, I would say, distributions of the local costs. When P is equal to 1, basically, you still can have one very costly local cost. If there are relatively few of them, or others are very small, your total energy may be small. As far as P, so this is what's happening here. When the P grows, especially grows to infinity, actually only the largest one plays a role. Whatever happens below is nothing. And actually in between is kind of going, kind of slowly drifting. When I was looking at this particular slide, it reminded me the problem that the standard graph cut algorithm, this kind of remark, if you don't know it, don't worry. There's a problem that of so-called shrinking. And people are trying to solve it by using normalized cut and so on. Possibly one way of doing it is take the standard thing and check for which piece the shrinking stops. Maybe even using some things. And of course, normalized cut has a problem. It's actually not a very efficient algorithm. Possibly you can calculate right P and do this in the standard way, so it will be more efficient algorithm and so on. So this kind of gives you the heuristic reasons for possibly doing some experimental checking what's going on. Okay, so let's check what's happening. Here I'm having this strange term NPcompleteness. As everybody knows, I will maybe tell you a few words. The class of so-called NP-complete problems is that there are many problems of this kind, and what's characteristic about them is that we know how to solve them using the exponential time of respective number of variables. We know that if you're lucky and we have a good guess, sometimes people call this guesses oracles, then you can solve this problem in the polynomial time. The big question, one of the biggest questions actually in optimization theory, whether this problems in a class of NP-complete actually can be solved always in polynomial time. To some extent, I remember the first, I've heard it when I was still undergrad student, this was relatively new, and people were trying to develop the complexity theory. Actually, we do have course about complexity theory, but actually it doesn't exist because the first problem that we found is this one. It has never been solved. So we have only kind of very. There are some. I call this cooking book. So there are some facts about the complexity theory, but we don't have actually. There's no even one good technique to show that something cannot be improved. We have only upper bounds. But there is no good technique to show that something has a lower bound. Solve this, you'll be the most famous person in computer science. I believe there's actually a big award for solving it. I mention this because at some point I will be touching this thing. Don't worry, my algorithm won't be exponential. But in some cases I will tell you, well, there are some troubles. So let's go here for this L1 where I started. And again, the reason I like, well, first of all, one of the most common cases is that you will use this in the situation where all vertices have cost 0, except few seeds that you kind of like to say what's going on. And then we talk about so-called graph cut. In a moment I will tell you what this, I'll remind you what this algorithm is. But in the standard situation, you assume that when you have the same labels, it will because the cost will be 0. When you have different labels, they are positive, actually, I believe that in general it can be oriented. It means either one or another. But very often we just say indifferently, and we look about this this situation. In this particular situation, there's a very good algorithm that probably all of you have seen, min-cut-max flow algorithm, that can actually find optimization of this problem. Okay. But notice that I impose here quite a few restrictions on how this local cost can be fixed. Okay. Here n is, so this form in this case, this is more or less what we know about the complexity. Okay, so not we don't have a lower bound because I told you there's actually no techniques of showing almost anything about lower bounds. What's known that when you know, even in this general setting, when you talk about more than two labels, the problem is what we call NPhard. What it means that if you could solve this problem, that you could solve the main problem, all others. So there's one direction of application. In general, when I talk about class of problems, let me tell you that this is kind of actual, the definition of equivalence is really done well by computer scientists. Equivalence means that we can have translation, but there's an algorithm that translates it, and the algorithm runs in polynomial time. So it's kind of very clear what it means. Okay. So when we have that something is NP-hard, it means that if we relax everything, well, I won't tell you that the polynomial algorithm doesn't exist, but if I found it, I'll be this famous person that solves the NP problem. So, well, there's some reason that maybe when you're early in your career, stay away from it. Okay.
When you're late in your career, you should stay away.
Well, no, I don't know. For a while, I've heard that mathematicians never actually die. They just start working on the Hilbert problem.
Okay.
Okay. So that for computer scientists, we can say the same thing. Yes. Okay. So what's known about it? Actually, in paper 2004, actually two computer scientists, Kolmogorov and Zaybich, asked when actually the very same algorithm, min-cut-max flow, can be used in the more relaxed situation. And they actually noticed that if any pair, for any edge, we have this inequality, that actually algorithms works fine, and it gives you the optimization. They also notice that if you put no restriction, that again it's NP-hard, so well, there's no real chance to solve it. Okay. This was more or less the situation that we started to look at this general problem. Actually, it is a relation between L1, LP, and L infinity. Actually, it was studied by several people. We have actually a very nice paper with Alexandre about this min-cut-max flow algorithm L1 and something that's called fuzzy connectors of watershed. They're kind of going in this direction, but they were in the kind of original settings. So what was happening is, look at this result, kind of very general settings, yes, and we know what's happening for p equal 1. What's happening for finite p, basically, if you raise each of these pieces, these local maps to the p, basically it's becoming L1. You just change the weights. Yes. So not surprisingly, if you have the same inequality, it's called as submodular, then min-cut-max flow still works. If it is not, if it's not. By the way, this submodality condition kind of looks strange Well, first of all, we didn't invent it. It was already in the paper of Kolmogorov and Zabich. But actually, this property was in some earlier research. I don't remember where, but even somewhere there is some physical interpretation of it even. So this was kind of naturally progressing. So, it isn't that somebody just come up, took a head of magician and pulled a rabbit out of it. No, it was kind of naturally appearing there. Okay, so now the question is, what's happening when p goes to infinity? Well, first of all, when p goes to infinity, you can argue that this condition kind of goes to this condition. And the Malbrook and Strand show in the conference proceedings that when you have both of this subnormality, then actually the mixed cut-max flow works correctly for all of these guys, and actually the results converges to the L infinity now. But this was still nothing that great. So this is more or less the end of the background. Actually, there's a little bit one extra remark that if you have for p large enough satisfy this condition, that also this condition holds. Okay. This was kind of the situation that we were at the beginning with. We really like to see what's happening with our L infinity norm in this general setup. And again, one of the reasons is because we know that actually in L infinity norm, a lot of algorithms actually work nicer. For example, in standard L1 case, I mentioned that there are almost no assumption when we have free objects, you can actually efficiently optimize. It is very easy done in L infinity. Okay, so the question is, okay, what we can do to get new? So this is our situation. This is our energy. Again, this is kind of repeating. And here I'm reminding you what's called, I call this here fuzzy connectedness. People sometimes call this watershed. So basically we assume that all labels of vertices are zero. So basically there are no unary costs. The binary cost is, again, when you have the same label, there's no penalty. Okay? And when you have different costs, I call this cut because this means that there's a difference between them. So the boundary is somewhere in between. Then we have actually something positive. In this particular case, we have very efficient algorithm that solves it. This is the Dijkstra algorithm or some other names. And it's basically a linear algorithm. Okay. So this was the question that we started to do. For what other situation? Here is the situation with the bullets. Can we apply this situation? This was more or less state of the knowledge, I believe, a little bit less than a year ago. So first of all, we noticed that if you get this natural modular arithmetic conditions, that how they come up with? Well, I just took a limit, and it's natural. But actually, there is an algorithm, and it is actually very efficient. It is also linear time or pseudo-linear. It means n log n. I will actually tell you a few words about how this algorithm works. There will be two algorithms here. They are all very simple. There are some difficulties to prove that they work, but implementation is really easy. Okay, and this is actually already published on the conference proceedings paper. I will tell you a little bit more about this, but there are kind of two natural questions when you have this thing. Is the assumption essential? In L1 cases, actually, the Kolmogorov and Zabich showed that it is. Well, we didn't know at that time, so started to play with it. And the second thing is, can we move this to the more than two colors? And again, like this algorithm works for more than 2 colors, min-cut flow not. So we had some hopes that maybe we have full positive answer in both, or at least one of them. Well, actually, I originally thought that the second condition is more likely to have positive than the first one. Actually, there's the other way around. Intuition don't always lead you where you like it to be. So, again, this is just a statement that tells you the full answer for this condition. I call this two satisfiability algorithm. In a moment, I'll tell you why. If you ever heard this term, two satisfiability, there is a reason I use this name. Basically, what it tells you is that there's algorithm a little bit more complex, a little bit higher, an n square, that returns two labeling that's optimum. So actually, our assumption was not essential. Well, if it was mathematical paper, I would say forget about the first one because I have here better results. But we like to have algorithms, and this one is a little bit less efficient. So actually both results have some value, at least we hope we have. So I told you there's not that much yet experimental usage of it. Okay. Again, I'll tell you a little bit more about this later, but what's the partial answer for question 2? And when I put it here, actually this conference proceedings invited some people to have the special issue of the journal of JMIV, and we hope that this will be in this particular paper. What we also found that unfortunately when you put the 3 labelings, and I will even give you a little bit understanding why that the problem is NPhard. So unfortunately, again, in general, we cannot do this. In particular cases, we can because the extra algorithm does it. We still don't know where is the line in between. This is actually something that might be interesting to study. This is very much research in progress. So basically, I just told you this what I just covered. We don't know where the boundary is. Again, everything I'm just repeating myself here. Okay, so let me just tell you, I usually don't like to put too many proofs, but this one is kind of sketchy of the proof. How do you prove that something's NPhard? Well, if you try to do this from scratch, it will be probably hard. There's a large number of problems that are just well known to be NPcomplete, so we know that they are hard. So one of the easiest ways just gives you a kind of setup and shows that you prove if by any chance you have polynomial algorithm to solve your problem, that you will solve another problem. If it's hard, then well, you'll have a hard time to find a good algorithm. Yes, and that's precisely what's happening. Let's just imagine that you take arbitrary graph, okay, and put all vertices cos 0. If you have the same, actually the same edges, same colors, it's 1. So you're actually penalizing to have an edge that's connecting the same color. And when they have different colors, there's no penalty. Now imagine that you're trying to optimize it. Well, it has a value 0 precisely. There's no edge connecting the same color vertices. This is the definition of what we call coloring of graph. You've heard about 4 coloring problem, one of the most famous one. That's it. But what is known, and again, I won't be proving you, that for 3 colors, this problem is NP-complete. If I could prove this for 3 labels, then I would solve a 3 coloring problem, and yeah, I would be happy, yeah, but this is the definition of being NP-hard. Okay? So as you see, even some proofs may not be that difficult. Okay? Okay. And interestingly, this is not the case for n equal 2. This was actually when we started to think about the first problem. Well, this argument doesn't work, so can we actually move this further. And actually, what's here happening? Actually, there's a, if you look for these things, we talk about free coloring problem is NPhard. Two coloring problem is not. Actually, it's a linear time. In quite a few cases, there's a big jump between 2 and 3. So we hope, well, okay, and I already told you that the problem has the positive answer for m equal 2. But what we did actually, our second algorithm is reducing to the old algorithm. So let me just tell you a little bit what is known about this two labeling. And again, I won't tell you everything in the proofs, but I'll tell you actually the algorithm is very simple. But what will be translating our problem, a big part of the problem, it's something that is called two satisfiability. Okay. In general, one of the almost canonical statement of problem this NPcomplete is that you take a formula of the what we call zero language. It means each variable is true or false. You connect them by conjunction, well, and or, okay, possible implication or negation. And the problem is, can you decide whether there's such assignment of truth that it will be holding? This is called satisfiability. This problem is known to be NP-complete. However, for some classes of formulas, it is known to be effective algorithm. So what we know? So our first things will be actually translating our two labeling into some kind of format for the truth. Before I even start doing it, I'll talk a little bit about actions, but think about it. The labeling, we were talking about 0 and 1. Well, truth has also usually consider 1 to be true and 0 is false. So we can have kind of natural identification of label 1 being true or label 0 being false. And that's basically what we'll be doing the translations. Okay. So in order to kind of do it, and my main question actually we'll be talking about is the following. I first define you an atom. And this is kind of, an atom is local information about our labeling. So what it means, for the vertex, atom will be 0 when the labeling is equal to 0. Okay? And for the, so this will be vertex and its actual label. Okay? For the edge, well, we have edge with their appropriate colors. These are the atoms of the actual labels. We can also talk about general atoms, all the atoms. So in general, we have for two labelings, 2 unar atoms. Yes, for each vertex, possible value 0, possible value 1. For each vertex, we have 4 possibilities. So here are the costs and so on. One of the major questions in our you can kind of imagine in the following algorithm that's more or less what we'll be doing. When we can start with all atoms, and our idea is try to prune them in such a way that we only get the atoms that are connected with just labeling. We have all atoms of the labeling that we can kind of naturally translate, take the union to be labeling. Okay. So basically what we need to do is decide which of these pieces of information we like to include, which not. So the basic question is which subsets of the atoms are good? Well, in what sense good? Well, good in the sense that they still allow some labeling inside. Yes, we call this they're consistent if within still we can, within the reduced possibilities, we can still find labeling. Yes, if we cannot, well, we're in bad shapes. Actually, this is the only thing that is needed for us to have an efficient algorithm. So actually, I'll now tell you the first algorithm. So we have this notion of being consistent. Consistent means that, well, there's still a solution within what we kind of reduced. Okay. So here's the general idea, and maybe before I will do it. If you try to, our energy is maximum of the cost, yes? So the higher cost, the worse it is. So what you should do, take all, enumerate all the atoms, and try to remove those of the highest cost. If you are succeeded, all others, and so on, so on. So the more expensive you remove, the better you are. That's basically how either of these atoms works. Well, you cannot remove all of them because then you will you like to be left with the labeling, and you don't like to be left empty-handed. Okay, so here's the idea. We in the first algorithm, and they both have pretty similar situation. We have we list all atoms in decreasing cost. You don't need to look at this. It tells you that if you do the increasing cost, it's not enough. You need to have some secondary condition that makes it a little bit more precise. Don't worry about it. I am just telling you there is a little extra simple condition. And do the following. Take our S is our kind of set of atoms within the site. Okay. There's actually, okay. Now remove this and look on the following. Well, basically, well, clearly, each vertex or edge have in general originally 2 or 4 cases. Yes, if you're left with everything but one, then you'll better keep this one, because after you remove it, you certainly won't have a consistent state. Okay. And if you have this, you can put this to list L. It is, we know that this will be part of our thing. And then what's happening? Like, so in order to do this, being for sure, what we need to know is that after we remove it, we can create the situation that we cannot remove any other atoms. So what we like to do, we have a clean situation. And this particular method tells you, after you remove something, you will probably have something called local inconsistency. An example is, for example, if you take a vertex, you will say, this vertex cannot have a label 0. Okay? If you still say have some atoms that are telling that the edge indicate that this would be 0, well, that's certainly not consistent. It will never happen. Yes? Because if the vertex cannot be 0, then the edge that indicates 0 cannot happen. Yes? That's basically what we call local inconsistency. We can kind of imagine that these are kind of very local things, so there's natural algorithm kind of naturally trim those things. That's more or less what we do. There's a little bit a question in what order we need to do it, but natural algorithm works. At the end, we actually keep only those that were unique. If you want to go to the end of the line, you are ending with the labeling. What's difficult, actually, there are 2 little difficult parts. It was coming out with a little bit order here, and a little bit order in which we need to do this. But actually, the most difficult part is not the implementation. It's proving that that's what we're getting there. That after we remove all local inconsistencies, actually, first of all, that our system is still consistent, but actually that is to some extent super consistent. So after we remove something, we're still in a good shape. Okay, so that's basically the algorithm. So it isn't very difficult. You just keep removing something, a little bit of information, ordering. This thing is actually very, very simple. So again, so that the trick is actually proving it. I like also to mention you that already with this setup, this assumption of infinite submodularity is actually not very strong. For example, if you take some standard Dijkstra-like algorithm and talk about oriented costs, no problem, it is still satisfied. We can do a little bit more than that. So it is likely that there was quite a bit of work in this group also, Paulo Miranda, about oriented graphs. Possibly some of the algorithms might be an alternative way of approaching this situation. Actually, Paulo Miranda also talks about cost of the cat. If you have the setup I was describing, his cost of the cat is actually precisely the cost of our labeling. So that's what we were doing there. So there are some examples actually that I could use it, but we didn't ourselves check the particular application. What's the second thing? I have only 4 slides. The second one tells you how to do this in general, and I'll go over this more only very quickly. It's very similar in the shapes, but for unit atoms, I like to associate the formula. So imagine that our vertex is now a variable of 4 formula that I can associate true and false. But surprisingly, the formula tells you that the formula is true and actually disagree with the truth rather than we agree. That's, for some reason, it's better. For the binary, we say that the formula is true at least one place we disagree. Okay? Then we can talk about what does mean that the set of atoms. For any set of atoms, we can define the formula, and we take either this guy or this guys and take, by end, conjunction of them. If you look at this is the formula that we have and, but the smaller ones are only alternatives of at most 2 that are very simple situation. Again, if you didn't see it, don't worry about it, but this particular situation is called 2-conjunctive normal form. And when we're talking about satisfiability, this particular satisfiability problem is well known to have a solution. What our theorem tells you is actually that the set of axioms is consistent if its complement, you look over the complement, looks for its formula, check satisfiability. So if you try to decide if the set of atoms is consistent, you're going to look on its complement, associate naturally the formula. That's, you don't need to see the how it is done precisely, but it's easy. Certainly it's easy. And decide whether it is satisfiable. The key here is that there is a very efficient algorithm that does it in a linear time. Okay. So what we did, we actually didn't create a new algorithm. We just told you that if you like to decide whether some sets of axioms atoms is consistent, that we can translate this, the old version and use some old trick. How to translate this into algorithm? Well, that's even easier than the first one. Again, these are atoms in decreasing cost. No extra assumption. And kind of take one atom at a time in this order. You remove this atom and see. Again, our L is what we already decided that it's non-removable. Look on the L and whatever is left. If it's not consistent, it means, well, we removed this atom, but we will better keep it, yes, because we're in trouble. So we are assuming that this is kept consistent all the time. So if it's not consistent, you put this to the labels. Otherwise, inconsistent, we'll move further. So what you're doing, we are removing in the decreasing order all the atoms that could be removed. The larger, the better. What we're left is what must be there. That's it. That's our labeling. Nothing difficult. The tricky part is this blue part. Well, yeah, that's an important part, but luckily it was solved, I don't know, 20 years ago, so we don't need to be worried about it. Okay. Now, can I have 5 more minutes, or I have 2 more kind of slides that touches slightly other, related, but other problems. But I can also stop here, so is it okay?
No, it's fine. I don't know if they have, are you going to open for questions now, or do you prefer to finish it?
It doesn't matter. The other thing is not,
It's
so,
fine. It's fine.
if you have a question, go ahead.
Do you have any questions about? My impression is that when you can you return to the yes. My impression is that are you assuming the way you remove the atoms from S? I mean, of course you have sorted them in the decreasing order, of course, but you're assuming this is. I mean, the way you remove them can be independent, right? So you can remove any atom.
Yeah. In this case, this is the only assumption. I like to from the most expensive to the lower, and each time you're kind of assuming that whatever is left plus this L, that's kind of or partial solution, that this thing is consistent. So try to remove the first one from not decided yet. Well, if you can remove it, just keep it. If you cannot, put this back to the L, the kind of partial solution.
I just imagine that problems that might appear, for example, when you have ties, right?
Well, we just proved that it is not. It doesn't create any problem. The ties doesn't create a problem because the ties doesn't influence actually the cost, because if you remove one atom of the same cost versus another, it's still the same. But everything else is done by these two, taken care of by these two satisfiability. We don't care which solution we obtain. If there is a solution, we are fine.
Okay. Yeah. No. Okay.
And so yeah, I understand actually your.
I'm thinking about ties between distant labels, for example, because as you remove, you're assuming that the one from that label, for example, for a unary cost, let's say, the one from label X, which is the last to be removed, as long as it does not interfere in the, as long as S union L is not consistent, this will be a solution, right?
Well, that if it is consistent still, then inside there will be a solution. So if there is a possibility there will be more than one optimal solution, okay? And actually, on next 2 slides, I like to slightly touch it. But all we know that we will get the minimizer. Is it going to be unique? No. And actually, this is one of the problems that I like to address in the 2 last slides. Okay. The problem is that basically, whenever we go below this maximum cost, actually, we have no control. Any of them is good. And you can kind of imagine that you have a lot of them of this maximal cost, or just one, and all others are better. So it seems that there should be a better way of measuring it. And this is kind of the standard way, the sharp distinguishing tool, something that they refer to as lexicographical order. So basically, look on the labeling, look on the all atoms, and kind of list their cost in the decreasing order. Okay. And what you like to have the smallest amount possible of the highest cost, then look on the next one and next one. So basically the way you can kind of talk about is the following. Count the number of the, look on this guys, look on the first place that they disagree, the highest, and the one that is, that's greater, we'll call this greater in lexicographical order. Basically you can imagine that the highest cost is like the first letter of alphabet, and you kind of count how many times it shows up. Yes, the second goes the second one. So you look on the first letter that they disagree, and this is the decision maker. So the question is, can you optimize? So if one labeling has better lexicographical order than another, then certainly in the max norm it is better, because the first place that they may agree in the first place that they have the same, or they disagree in the first place, then that one is actually better than another. So this is basically a sharper tool, and when you use these things, there's considerably lesser chance that two labelings will have the same cost. Okay, so this kind of if we could actually get optimization in this way, we will have very few ties only in subsets. Okay, so we have this. So the question is, can we find optimal, the reasonable algorithm that still do it? And my last slide is just a table telling you that some cases you can, in some cases you can't. I'll very quickly go over them, just to give you some idea what's happening. That inside and so on. So here's the case. If the general case means no restriction, if you like this to be strict optimal, which is lexicographic, in general we are hopeless. Everything is NP-complete. If you add a submodularity, that actually it is done, and it is done by standard max flow min cut. Well, I need to kind of do a little bit of changing the weights and so on, but basically it can be done in the more or less quadratic plus time. Actually, this is a strong assumption. If the weights are unique, it means every atom has its different weight, that our new solution of and square time also provides the good guy. Unfortunately, this unique weight is a pretty strong assumption. Okay. When we don't like to strict, this is kind of summary. The general case, everything is fine. So far, there's nothing good in the 3 and more labels. Again, when you have submodular, we have also a better solution, but with better complexity. Still nothing good here. And the only good here we can have is basically in our Dijkstra algorithm. And this is the only case that we have something for more than 3 and more labels. Okay, that's about what's the state. There are actually some questions about what can be done in this case, especially what's happening with 3 and more labels, very little is known. And finding the actual application would be nice, because we have some idea that some other application can be translated into this framework, but we didn't actually make any experimentals yet. I'll just go over it. Let's just.
Questions? Okay.
In this context, you aren't worried about the complex, about ordering the atoms in itself. Because if you don't have a linear time to solve the problem of labeling...
Well, when I talk linear, I always call this quasi-linear. I sometimes use the incorrect language of linear, but I always was writing n log ln of n.
All right.
So, in one case, there's only one case there that I believe is truly linear, and this is this two-satisfiability problem. I believe this is truly linear, but even here I didn't check this that carefully yet.
So yeah, even if that step of the algorithm is linear, you still have to order the atoms, so that part will be...
Well, we call this quasi-linear.
Yes, I see.
Yeah.
All right.
Okay.
And another part, on that table you show the strict condition. That means it follows the lexicographic order.
Yeah, the strict means optimal with respect to the lexicographical order.
Oh, I see.
This
I
is
was
kind of
wondering, because you are ordering things. If you just find some way like a small epsilon that differentiates the weight of each label, so that you have an order relative one to each other.
well.
You use the same algorithm.
I'm not sure what you're talking about. You're meaning in which case you were talking about?
Show the lexicographical part.
Yeah. Well, but basically this discuss anything to do. So
Show the slide where you talk about lexicograph order.
okay.
So the problem there is that because different labels can have the same weight
Yeah.
and multiple optimal solutions, right?
That's right.
So you just find some way to different the weight of different labels, so force a given order.
Yeah, that's one of the. Well, let's go back there for a moment. We can we talk about these unique weights. You can do a small deviation of them.
So that's the idea.
And that's what we make sure. But when I say this is a strong assumption, yeah, you can deviate it, optimize it, and then just forget about deviation and look at the resolution. The problem is that this undeviated solution doesn't need to be optimized. Optimal in general.
I understand. All right.
So that's why I called strong. Yeah, you can kind of reduce your problem. This will be not precisely the same problem.
Yeah, that makes sense. All right.
Okay.
Okay. Other questions? Chris,
Sure.
when you can, in the case of, let's say, using, no, I have actually two questions. One is the cost to verify if L union S is inconsistent. Is that constant type? Because all you have to do is to...
You're talking, let me just go back for a moment to this algorithm and I'll tell you what I know about it. When we talk, when we're talking about asphalt et al. Algorithm, actually one of the reasons we didn't implement this is, I believe in the original asphalt it was basically really linear, maybe quasi-linear. But we didn't implement this because there's some new result that actually does this dynamically. And I think, at least what Philip tells you, that it can be done more efficiently. If so, possibly our n square can be improved. We didn't still study of the better way of doing this to satisfiability. We know it's reasonable good, but that's more or less all we know.
Okay, and the other question is, what about, can I, because you mentioned in the end, that let's say if you have more than 3 labels, right?
Yeah.
And then suppose that you have your graph here, so you have all binary terms, right? And you also connect, you have one representative virtual node for each object.
Yeah, that's one of the way of looking at this.
Yeah. And then you have edges that connect that virtual node to all image pixels, which are the unary costs. Right?
Yeah, that's one of the way of looking at this, yes.
But in this case, the unary cost, you would have an edge between every node of the graph and every object, right?
It means, notice that, I'll tell you, the way I stated, I never said you how many edges the graph has. I kind of implied that this is the standard way we do this image processing, but none of this theory tells you what kind of graph you have. So you can add a lot of edges, but actually you can have very sparse graph.
That's fine. So for example, if you have k objects, you could have k edges, k unary cost, of course.
Yeah.
So every element with respect to every object. And then if you set this, and then you run Dijkstra, for example, by placing those virtual nodes into, or even all nodes into the priority queue, let's say, or the virtual nodes into priority queue, and execute one Dijkstra algorithm from them, And so each of these virtual nodes will create one optimal path 3. Say.
Well,
can you connect this to the...
Well, first of all, let me tell you, when you talk about this optimization, because in principle doesn't need to have anything to do with the cost of the path. It is relatively easy to translate the cost of the cut with this energy, but actually there's no easy way to think about this in the term of the cost of the path.
Yeah, I believe that if you implement Dash this way I'm describing, it's possible to prove that the cost of the cut, the optimal cost of the cut, is the one that you were talking about.
Well,
although the algorithm is also minimizing the cost of the
no,
path.
if you have under the assumption that basically vertices are, well, very few ways basically connect with the seeds, and basically what I did initially, same label has no cost, 0. Then Dijkstra will work, yes. And there's we actually proved this in one of our earlier versions that path optimization is equivalent to the minimization of this cost of the path. Yes, this is well known, it's proved, and so on. But here we are giving more. You need some extra assumption to this proof.
But what I'm saying is that you don't actually need seeds as hard constraints.
Well, yeah.
You can use, let's say, the virtual nodes that represent each object.
That's right. Actually, unary costs, the way you usually think about seeds, you give some kind of infinite or minus infinity costs, and these are hard constraints. But you can make them, soft. The other thing is, when you talk about, for example, in even Dijkstra set of algorithms, we talk about classical edge constraints like homogeneity-based affinity, difference of intensities. There's also what we call object-based affinity, that's basically for the vertex. For example, it's a difference of the intensity to the desired intensity. We always, in the Dijkstra, had to squeeze this object feature to the edge, because we didn't have any tools. Well, this might be a possible tool to deal with it, okay, somehow differently treat them.
No, that's what I'm thinking, but I think this way, I mean...
Yeah. It means I don't know precisely what will be experimental results, but I think this is very much worth to checking experimentally.
Compare and see which one is the best way to combine.
That's right. And there was actually some question in São Paulo, I was talking about it. People were worried get a connected sets to the seeds. It isn't that obvious in the way we do it, but if you think about it, imagine that you have kind of a hole somewhere, yes? So you have some extra boundary. Remove it, actually your cost will never increase. You're actually going to decrease it. So the answer is the standard way it will be connected.
Yeah, if you have hard constraints, let's say seeds, hard seeds, right, inside the objects, I think it's possible to do with no disconnectivity. But if you have like only object nodes, no seeds, then it might get because it will depend on the
remember that the seeds are just one way, but even if you have no cost of the even if you have no cost of the seeds, all the seeds are 0. The vertices can prevent you to have just one object, because the cost of the vertices is still very much hardwired. Well, you probably think that label 0, 0 always has a cost 0, and in this case, it would be just one object, label 1 everywhere. This would work. But we are making some assumption.
I just imagine that the relation in terms of magnitude between the binary costs and the unary costs might cause this kind of problem.
Yeah, it might. Here we were talking about maximum, but we can go back to the original L1 that Zabich and Kolmogorov were doing.
That won't happen.
and you can actually add them, kind of do easily the modification. Also, in their case, it's obvious that all regions will be connected and actually be what we call simple connected. Because, that's basically clear unless, if you can get a boundary of cost 0, that it would not be the case, but I'm assuming.
Yeah, if you don't have hard constraints like seeds, the solution of Zabi obtain this connection.
Yeah.
It's like a thresholding sometimes.
Well,
in the sense that whatever is similar to the object becomes object.
Basically, you can get a hard constraint, but you can probably make a soft constraint. And I still not have a good feeling, where and how precisely to do it.
We can discuss that better because I have some ideas how to do that without the hard constraints, but we need to discuss. Yeah.
I'll tell you, when I was reading original paper with Abi and Kolmogorov, I remember that around this time, either in this paper or someone nearby, they had actually application of it. And they were actually kind of very, very interesting. So they were application that actually had, I believe, soft seeds and some kind of strange. I believe they had variance between whatever called vertical edges and horizontal edges, and they were getting some kind of nice statements. So you have a lot of flexibility in the setting. But again, this is something I hope maybe your group will work on.
Yeah, let's do that.
Okay.
Okay, so anyone else? Any questions? Well, at least the way you presented here, it looks like apart from the sorting, I mean, we can do parallelization, right?
Yeah, actually, yeah. The first algorithm, part of sorting, is easy because it's only local. In the other one, there's this two satisfiability, and two satisfiability. I'll tell you, it is more or less finding the connected component in directed graph. So this is pseudo Dijkstra, and there are some difficulties with it.
Okay.
So I won't tell you it can be done. This is, let's say, a work in progress.
So let's thank you again.
Okay, thank you. Let's turn this on.
Ele queria conversar contigo. Ele queria conversar contigo. 10 minutos. Uma pergunta que você fez para ele.
Ciekawe, ja to nie jest moje. Mam wyłączyć to?
Tego. I just like to have a very, very short word.
Ja się muszę pożegnać. Bo bardzo mnie spotkać. Mam nadzieję, że spotkamy na końcu.
I just want to tell you, we're talking about whether this summation function will always end up. It is a relatively simple argument that there's no infinite loop.
Great.
I can either, it depends on what will be there, I can either tell you this more or less in 5 minutes. It's actually easy. Or if there's a lot, I don't know what's your time, but just be aware.
I have to go back, but we can talk for 5 minutes.
Well, I'll tell you what's actually the arguments are relatively simple. The only time it doesn't matter in what order you take your spots. The only time you actually